Okay, students, so welcome to our first proper remote learning lesson, first lesson of differentiation, and our inquiry this time is going to be what can differentiation tell us about types of change. This might be a slightly longer video and slightly longer lesson than normal. I'm interested in your feedback about how it goes, and there'll be a little survey at the end. Along the way, I'll try and explain a couple of the things we're doing because I see it working the same way for most of our lessons. So, first up, if you've not done so already, what I'd like you to do is to consider the questions on the first slide here. What is differentiation? How do we interpret dy by dx? What does that actually mean? How is that different from a related expression, dy by dt? And when we use the language rate of change, what do we mean? So these questions are going to be fundamental to what we study, and as you're thinking about those, the first activity I want you to do is via Desmos. So you can see here on this screen, there's a URL there, and there is a Desmos class code. This will lead you to a very quick series of questions online that relate to differentiation and where it comes from. So I'd like you to pause the video now. I'd like you to go to that URL and complete those questions, and I will see your responses through the teacher view at the end. So pause your video now. Okay, so hopefully you've completed those activities. I look forward to seeing what you're doing. And before we jump into the maths, there's another thing that I'd like you to do. And this was in the notes for the lesson. So if you haven't already done it, to recap about differentiation, what it's all about, I'd like you to look at the history a little bit. So there's two videos here, calculus controversy and a rap battle. They're quite short, and I'd like you to watch both of them. In the quiz we do at the end of this lesson, there'll be a couple of questions based on what's in the videos. The URLs are in the Google Classroom. Okay, so you've watched those videos, and hopefully it's recapped a little bit and maybe taught you something new about the idea behind calculus and where it comes from. And in our first lesson today, most of what we're doing is recapping from math methods, the rules of differentiation that we should know and be quite familiar with, and we're going to introduce one or two new things. In terms of your contract, you hopefully have got a copy of this easily to hand anyway, but if not, these are the questions that you need to complete. So after today's lesson, from 6A, 5, 7, 8, 9, 10, 11, and 13. Okay. So, to our booklet, and I'm going to pause or ask you to pause the video at various points through this, and just like we do in class, ask you to have a think and to fill in the gaps before I go through them. That's really important because if you're just passively listening to me, your engagement will be shallower, your memory will be poorer. Much better, as much as you can, for you to think these things through yourself and then check your answers with me afterwards. But to begin with, hopefully informed by that Desmos activity, we're just going to talk briefly about differentiation from first principles. And this should be something that you've covered as part of maths methods. So differentiation is the idea of trying to find the rate of change of a graph with respect to a different variable. And on a graph, that would be the independent variable x, and the rate of change is the gradient of the curve. And what we imagine is finding the gradients of chords that originate at the point we're interested in, and we make the width of the chord smaller and smaller and smaller, and look at what happens to the gradient of the chord as we follow that process. Now, a mathematical notation for that is, first of all, we have the gradient of a chord. So that would be the change in y, or the rise, over the run, or the change in x, because we're imagining a chord with a run of h that runs from x to x plus h, and with y coordinates of f of x and f of x plus h. Now we imagine, or we define that to be the gradient of the chord, which hopefully we're comfortable with, and what we look at is the limit as h tends to 0 of this thing. And in that Desmos activity, you followed that process. You calculated the gradient of chords where h got smaller and smaller, and considered what would happen as h tended towards 0, as it got closer and closer to 0. This function, when defined for different values of x, is known as the gradient function, or f dash. And by examining this, by following this process of looking at the limit from first principles, we developed different rules for different functions that then we can apply without having to go back to first principles all the time. But it's worth always starting a conversation about differentiation with the first principles argument, with this idea that the chords are getting smaller and smaller, and it reminds us that we can actually think geometrically about this, and if we're trying to find the gradient and we're thinking about this diagram here, we could think about it in terms of the angle theta, because the gradient of that tangent line is going to be the rise over the run, the change in y over the change in x, which would be tan theta. So we have to be prepared in differentiation questions always to take things back to first principles, but the rules that are our real building blocks, our standard derivatives from math methods, also are used extensively in specialist maths. So I'd like you to pause the video now, and in the box at the bottom of the page here, I'd like you to have a go in pencil at filling in the derivatives of these standard functions, and then also the 3 standard rules that we're supposed to know. Pause the video now. Okay, so you've paused the video, and let's have a look. The derivative of a constant is always 0, because a constant is a horizontal line. If I've got a polynomial, my standard rule is that I reduce the power by 1 and I multiply by the power. So our gradient would be an or na x to the power n minus 1. We notice here that this works for all powers apart from 0, including negative powers and including fractional powers. If I've got trigonometry, the k that's inside the bracket will always come out, and if I just think about the graphs, the gradient of sine starts positive, a gradient of 1, and then it decreases to negative, reminding me that the gradient must just be cos kx. But if I think about cos, and I think about the gradient of that graph, the gradient must start at 0, but it's straight away negative as that cos function comes down, which reminds me that there is a minus sign involved, and the gradient of cos kx is minus k sine kx. This idea of the k's coming down in front is really common. If I've got an exponential, that's all there is to it. The derivative of an exponential function e to the power kx is just k e to the power kx. And then the final one of our standard building blocks is about the natural log of x, only defined for when x is greater than 0, and hopefully it's familiar to you that the gradient of that is 1 over x. If you're unclear about any of this, hit your math methods books again and have another look at these types of questions, because it's really important as we go into specialist maths that you're very confident on this. In terms of the rules you've learned in math methods, there are 3. We have the product rule, we have the quotient rule, and we have the chain rule. And what we need to be good at is moving between different types of notation. So I'm going to write both here. On the left hand side we have standard function notation with f's, g's and h's, and on the right hand side we have a slightly leaner version where we write those functions as u and v, and we assume that they are in terms of x for the most part. So the product rule, when we multiply two functions, well, it's the derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. And there is some symmetry to that. Another way to write it then would be the first multiplied by the derivative of the second, dv by dx, plus the second multiplied by the derivative of the first. Those are exactly equivalent. The quotient rule, quotient meaning fraction or division, we have g of x divided by h of x. And the derivation of this, if you've not done it using in drawing maths methods, is to do the product rule but making the second function a reciprocal, so to the power -1. And if you've not done that, you want to work through it, you can prove the quotient rule using the product rule, but what it gives us is a standard form that we can remember that saves us from having to go through that process every time. And it's a fraction. The numerator is similar to the product rule, but we have a minus sign. So it's the derivative of the first multiplied by the second minus the first multiplied by the derivative of the second, and then it's all over the denominator squared, h of x squared. My favourite way of remembering this is in terms of u's and v's, and what I would always say is it's v du minus u dv all over v squared, and then afterwards I can fill in the dx's. So v du minus u dv all over v squared gives us the quotient rule. And then the last one is the chain rule, which is for nested functions, a function within a function. So here we have h being the outside function and g being the inside function, and we can see the nested brackets. In this case, the gradient of the whole thing, well, we take the derivative of the inside function and we multiply it by the derivative of the outside function with the inside function still inside it. So both derivatives, but the outside function still contains the inside function. A second way of writing this is to actually say, well, look, if y can be rewritten as a function of u, where u is the inside function g of x, then we can actually do the differentiation in two parts. We'll come back to this. We can say that dy by dx is the same as dy by du. So the differentiation of the first function here multiplied by the derivative of the second function du by dx. And one thing that I don't know if you've talked about before, but that's quite pleasing about this, is a bit of notation, is that there's a little bit of fractional cancelling going on here that is intuitive. It's not, we have to be a little bit careful with this when we're talking about derivatives. They're not actually fractions because they're the result of a limit, but the notation is helpful because we can use some of these shortcuts with fractions. So we can say that dy by dx is clearly the same as dy by du by dx because the du's cancel. Okay, so like I said before, if you are a bit rusty on all of this, then go back and do some maths methods practice, get yourself up to speed. Otherwise, what I'd like you to do is flip over and try the first three questions here. One example of the product rule, one example of the quotient rule, one example of the chain rule.